Okay, so what we're going to look at is a thing called stoichiometry, or counting atoms, or finding amounts of stuff, or masses of things. So you see this word quite a bit in what we're doing in the next week. Really, it's about counting and calculating using these two ideas here. But before we can go any further, these are the page references from beginning chemistry that have this information backed up and some exercises to go with it. Before we go into this though, we're going to go back to what I described as our Bible of chemistry, which is the periodic table. And on the periodic table we see some numbers. So for example, if I look at, let's take chlorine. Chlorine's got two numbers next to it. If I look at the picture of chlorine, it's got a 17 quite often there, or it might be central. And then underneath in smaller writing is often, and if I get the number wrong I apologise, 35.45 might be written there. Okay. This number here, if you start counting along the periodic table, you see that it actually is the 17th element. So it's what we call the atomic number, or it's given the symbol Z. So this thing here is called Z, or the atomic number. We should know that this equals the number of protons, and for the atom, it's the number of electrons. From that, we can work out its electron configuration and work out that it makes either one covalent bond or becomes a negative one ion. So we can learn a bit from Z. It teaches us quite a bit. I'm not worried about that for now. This number at the bottom, though, is really important. It's called A. And because it's not just a number, it's got decimal points after it, it's called A with a subscript capital R. And it means relative atomic mass. Now, I'm not going to write a definition for that because you don't need to say that verbatim, and I'll probably get it wrong if I try to do it verbatim. Basically, what happens is if we get the isotope of carbon that is called carbon-12, and we get a certain number of atoms of it, 6.023 times 10 to the power of 23, it's called a mole. I don't know where they got the word from, and I've never really worried, but it's called a mole. So if I had a mole of carbon-12, it has a mass of 12 grams. If I had the same amount of atoms, same number of atoms, so a mole of atoms, if I had 6.023 times 10 to the power of 23 chlorine atoms, it would have a mass of 35.45 grams. Now, the reason that it's not a whole number, and this could be asked in a question in another unit in structure and bonding. The reason that these are not whole numbers is because the isotopes exist of chlorine. There's chlorine that's got a mass of 35, so 18 neutrons, and there's chlorine 37, which has 20 neutrons. Because it's so close to 35, that tells us that the 35 chlorine is more common than the 37 chlorine. If it was at 36 and I knew that those two isotopes existed, it would be an equal ratio. So it tells you that there's more 35, chlorine 35, than any other isotope of chlorine. But it means that if I have exactly what we call 1 mole of it, then it's got a mass of 35.45 grams. Why are these numbers important? Well, they actually help us predict whether our reactions are going to work or not, because you need a certain amount of reagents, or actually this amount, number of atoms present, to make things happen. And we know that by doing a balanced equation, which is something we've already worked on. Okay? But we don't normally react atoms, mainly because not a lot exists as atoms. The noble gases do, and that's about all. Metals exist as metals, so that's their cations and a sea of valence electrons. Most non-metals exist as molecules. So chlorine is actually Cl2, it's got 2 chlorine atoms together, it's not just one, that sort of thing. So we really work with atoms. So instead what we actually work out are our relative atomic masses. That probably should have a little subscript R on those as well, but we said another way given. And we work out our mass of a compound or a molecule by adding up these AR values from our periodic table. So therefore, if I wanted to find the molar mass of a chlorine molecule, which is what the element exists as, I have to go sigma, which means adding up the total of, so it's sum of the relative atomic masses. And because they're the same mass, it makes it quite easy. That means that I'm going 35.45 plus 35.45, which equals 70.90. And it does have a unit, grams per mole. So that is the mass in grams of 1 mole of the stuff. Have I done my maths right? Yes. So, this is the molar mass of chlorine. Now, if my chemical reaction, my equation that I've balanced, says that I need to have in my reaction 2 moles of chlorine for this reaction to go ahead. So, for example, H2 plus Cl2 going to 2 HCl's, if I needed twice as much as what I've just described there, then I know the mass of chlorine that I need. And by working out the molar mass of hydrogen, I know the mass of hydrogen I need as well. So the next thing that we get is this little equation here at the very top, which often is easier to remember as a triangle. You know how you remember F equals ma, so Newton's second law of motion? Often as a triangle, you cover the one you're trying to work out with your thumb. This one works really nicely for that as well. So what you'll see is it's often drawn like this. And I'm not going to put the R's in it because I've got a little way to remember it. Because they're both M's, so it's hard to remember. N equals M over M. I don't know about you, but my brain doesn't know which one of those is capital letter and which one is a small letter if I just say it to myself. I might yell, I might go, N equals M over M! But my brain still doesn't really know, it just scares itself. So, instead, here's a little saying for it. A capital M to me looks like a mountain range. That's how when I was a child I drew mountains. Here's a reminder of my wonderful mountain range. Here's the snow line. Okay? And when I was little, I used to draw birds like this. And birds fly over mountain ranges to get somewhere else. The little end, the bird, seagull, flies over the mountains. So there's another way to remember it, if you need it. You're not given that in your assessment. You need to remember it off by heart. Okay, that's why I'm giving you a childish little trick to remember it. Okay, so how do I use it? If I've got my balanced equation, and from that balanced equation, I know how many moles I need. So let's say for argument's sake I need 2 moles of chlorine in the following equation. So I've got H2 plus Cl2 goes to, so it's an arrow not an equals, 2 HCl. And let's say just by doing some other calculations, I was told that we've got 2 moles, which is a certain amount, large amount by the way, 2 moles of hydrogen. What that means is because it's a balanced equation, there's no number in front of hydrogen, there's no number in front of chlorine, I also need 2 moles of chlorine. Can anyone guess how many moles of HCl gas this would make? If this is 2 and this is 2, spot on, 4. But be careful. The common error is, that plus that equals that. That's not true. It's 4 because this has got a 2 in front of it. Okay, it's 4 because this has got a 2 in front of it. It means if this was 1, this is 1, this is 2. If this was 10, this would be 10, this would be 20. It's because of the number in front, it's not because 2 plus 2 equals 4. That's not how it works. You see that with more complicated equations, such as this is called the Haber process. It's got a funny arrow that goes backwards and forwards. That's an H, sorry. This just means it's an equilibrium. It means the forward reaction happens and so does the backwards one. Just double check my maths. Yes. If I had 2 moles of nitrogen, how many moles of hydrogen would I need? That's because the 3 is what we look at. I'd need 6. If there's 2 of that and there's only 1 in the equation, then there must be 6 of those. So 1 of those, 3 of those, 2 of those. So therefore, multiply everything by 2 like you do in maths a lot of times with algebra. So if that's 2, That's 6. And actually, you'd expect it to be 8, wouldn't you? But it's not. 2 moles of that plus 6 moles of that makes 4 moles of that. Again, it's because of the 2 in front. See how that's 4 moles? And that's 4 moles. That had a 2 in front, that had a 2 in front. So, using the same idea, I'm going to harp on with this one a bit because it's so important. If I had half a mole of hydrogen, how many moles of chlorine would that react with completely? Brave and call it out. Half equivalent. How many moles of HCl would it make? Brilliant, 1 mole. Okay. So, let's use the same rule. If I had half a mole of nitrogen, how many moles of hydrogen will that react with? 1.5. Fantastic, 1.5. And how many moles of nitrogen will it make? Oh, sorry, of ammonia. Sorry. How many moles of ammonia will that make? 1. Perfect. So I'm hoping now you're taking the one that you do know that's got no number in front of it and just multiplying it by the number in front of these molecules. I'm hoping. And if not, you will have to watch the video a couple of times. So 1